Good afternoon, everyone. I'm Pauline Martin, and I will present you today some results we got with my colleagues Nicolas Frigans, Vincent Ducrot, Philippe Faverdin, and Daniel Gordeau from the GeneTour and Défilé projects that leads us to develop a new method to estimate RFI in the recadle using time series data. Let's start with what exactly RFI is. RFI stands for residual feed intake, which is one of the multiple criteria that exist to define feed efficiency. This is the difference between an actual intake and an intake that is predicted from performances. This is usually the residual from a linear regression. So you get on the left side of the equation the intake, and on the right side a regression that is based on milk, weight, body condition, and the residual that is the RFI. As I told you, this is a linear regression, so the coefficient little a, b, and c here are fixed and remain stable all lactation long. But the problem is that the lactation is a dynamic process, and if you neglect to take into account this point and the lactation stages, you get naive assessment of RFI. And this brings us to the main point of this presentation, which is, can we adapt the RFI methodology to include the dynamic dimension of lactation into the estimation? To answer this question, we used the data from the University of Aarhus experimental farm. So the data were collected between 2002 and 2016 on Holstein cows, and they were from a little bit more than 1,000 lactation from 564 cows, and the data were from first to third lactations. We had weekly information for milk quantity and composition, which lead us to compute a trait called corrected milk. We had the dry matter intake, the body weight, and the body condition score every 2 weeks. All the lactation that we kept were recorded for a period of at least 200 days. On this data, we applied a multi-traits random regression model. So on the 4 traits that we defined before, intake, milk, or corrected milk, weight, and body condition score. So the model was as follows, with on the left part of the equation the observation for each of the traits. On the right side, we had a fixed effect that corresponds to the contemporary group with a month-year combination. Fixed regression part that was to fit the model within each parity class. Random regression part that correspond to the animal effect, and residual. So for this equation we use Legendre polynomials that were evaluated in milk. And what is important to get in mind is that the animal effect includes both genetic and permanent environmental effects. And to perform this analysis, we used the Wombat software. What do we get out of this model? First of all, we get solutions for each individual. When we combine them with the coefficients for each time, the Legendre polynomial coefficients, we get an animal effect for each time, each individual, and for the 4 traits. So it allows us to calculate the repeatability of each trait across the lactation. What else do we get? We get a variance-covariance matrix, which is of size 12 by 12, because we have 3 coefficients and 4 traits. And when we multiply this matrix by the time coefficients, we get a 4 by 4 matrix for each time. So as you can see here, we have the variance on the diagonal and the covariance on the 2 sides. We can use this matrix for another writing with A submatrix that we will use later. So with this matrix of variance covariance, we can calculate the correlations between traits at each time, or also the correlation within traits between times, or a mix of the two possibilities. And finally, by using both the variance covariance matrix and the animal effects for each trait, it's possible to predict an animal effect for intake by a regression of the tree of traits and variance covariance relations between traits. So by the formula that is on this slide, and once we get a predicted intake, we can use the difference between the actual animal effect for intake and the predicted animal effect for intake to compute RFI. So we end up with RFI value for each animal at each time. If we go now to the results and start with the RFI itself, we can see that our definition of RFI shows the same characteristics as the classical RFI, with a mean at 0 at each time point and a phenotypic independence from its predictor. But you can also see that the RFI is not constant all lactation long, with here 4 individuals as example. As you can see, for the red individual, it is an inefficient animal during all the lactation. On the other hand, the blue animal starts being inefficient and switch to efficient for the end of the lactation. This is the contrary for the yellow, which starts being efficient and is inefficient middle and late lactation. At the end, the gray animal remain efficient all lactation long. Measure the RFI all lactation long is not always easy to do in practice. So is there a period in the lactation where it's the best time to measure the RFI and give an overview of the efficiency of the animal? So to get the answer for that, we estimated the correlation between daily RFI and an RFI average on all the lactation. And so we get that the correlation is always positive, but it's maximum during mid-lactation, where all the biological processes remain more or less stable. So if you want to measure RFI only in a short period of time, you can go for mid-lactation and you will get more or less the same ranking of your animal as if you were measuring on all lactation long. Now that we get a dynamic RFI, we can ask how does our method compare with classical methods. So to answer this question, we got data from another farm, the Mesusome experimental farm from France, where 205 lactations were available. For this animal, 2 classical linear RFI were calculated, one from dozen milk 1 to 148, and the second one on the period running from dozen milk 71 to 148. And for these 2 periods, we compared the RFI that were estimated with our methods and the classical methods. So here are only preliminary results, but the correlation was pretty high in both cases, with a correlation of around 0.6 for the beginning and mid-lactation together, and of 0.7 if we consider only mid-lactation. The last point was the possibility to combine datasets. So also with the Measure data, we perform two analyses with our model. One only with the data from Measure and one with the data from Measure combined with the data from ARUS. And for the Measure animals, the RFI that was estimated in the two situations was almost the same, with a correlation of 0.95. So there was almost no re-ranking when the two datasets are combined, which increased the possibility of use of the model because we can now use it on datasets that are too small to be run on themselves alone. And also it allowed the possibility of the use of this model for genetic selection. In conclusion, we have now a new method to estimate the RFI that is able to follow biological changes through the lactation by giving a RFI at each time. This model manages well punctual missing data, but cannot predict when entire parts of the lactation are missing. As this is a multi-trait random regression, we need a lot of data to compute. But it's possible to mix datasets without changing animal ranking within each of the datasets, so it's also the possibility to use it for genomic selection. At the end, the model compares relatively well to linear RFI estimation mid-lactation, but show larger differences when early lactation is included too. Details for these results are available on demand or in the two papers that we wrote on the subject, and thank you for your attention.